Hello, my name is Ahmet Utku Özçelik and this is my project video for Physics 102 lab. In this experiment, my aim was to find the magnetic field strength on a point between two magnets by utilizing the Hall effect. Here is the Hall measurement apparatus. It has two important sets of ports. The IH ports are for feeding the current to the sensor, and the VH ports are for measuring the Hall voltage that develops across it. In our setup, we connect the DC power supply to the IH ports to control the current precisely. Meanwhile, a multimeter is connected to the VH ports to measure the resulting Hall voltage. Two magnets are placed on either side of the sensor to create a uniform magnetic field. Additionally, we use a Gauss meter to independently measure the magnetic field strength for comparison. Now, let's talk about the physics behind the experiment. When an electric current flows through a conductor placed inside a magnetic field, the moving charges inside the conductor experience a magnetic force. This is called the Lorentz force. As a result, the charges are pushed sideways, causing an accumulation of charge on the edge of the conductor. This separation creates a measurable voltage across the conductor, known as the Hall voltage. The Hall voltage VH is given by the relation VH equals IB over NTE, where I is the current through the conductor, B is the magnetic field strength, N is the charge carrier density, E is the elementary charge, and the T is the thickness of the conductor. This formula shows that VH is directly proportional to I, meaning that if we plot VH versus I, we should get a straight line. From the slope of this line and knowing the material constants, we can calculate the magnetic field strength B. In short, the Hall effect allows us to measure the strength of a magnetic field just by measuring voltages and currents. After collecting data for different current values, we plotted the Hall voltage versus current graphs for two different magnet distances, 2.5 cm and 2 cm. For the 2.5 cm setup, the slope of the VH versus I graph was found to be 186.4 volts per ampere. Using the Hall effect formula, this gives a magnetic field strength of 149.1 militesla. For the 2 cm setup, the slope was slightly higher, 193.2 volts per ampere, which corresponds to a magnetic field strength of 154.6 militesla. We then compared these experimental values with the magnetic field measurements taken directly by a Gauss meter. The expected magnetic field strengths were 136.2 militesla and 161.6 militesla respectively. The percentage errors were calculated as 9.5% for the 2.5 cm setup and 4.3% for the 2 cm setup. These errors can mainly be explained by three factors. First, it's difficult to perfectly align the Hall sensor and the Gauss meter probe at exactly the same point, which can lead to slight differences. Second, internal measurement errors exist in devices like multimeter and Gauss meter themselves. And third, the Hall apparatus might have small imperfections, such as slight difference from the assumed internal resistance. Overall, these errors are within a reasonable limits, and the experiment successfully confirms the theoretical predictions of the Hall effect. Despite errors, the data show excellent linearity, confirming the Hall effect's prediction that VH is directly proportional to I. The steeper slope at 2 cm reflects a stronger local magnetic field, as expected when magnets are closer. This consistency validates both our method and the underlying physics. In summary, we successfully used the Hall effect to quantify magnetic fields with better than 10% accuracy. Thank you for watching.